Could some of the most intriguing mysteries of our solar system be hidden not within the massive planets or luminous stars, as one might assume, but perhaps within the cosmic dust, ices, and abyssal darkness of space? Yes, within asteroids. These seemingly small and unremarkable celestial bodies might actually each be a time capsule. They existed somewhere out there before Earth was even formed. From the moment they were first observed until today, they have remained unmixed with anything, preserving within them the mystery of their initial formation. If we had the chance to open these time capsules, we might not only better understand how the solar system formed, but perhaps even grasp the origins of humanity. Given the importance of this, NASA's interest in asteroids is hardly surprising. To date, many missions have been conducted to image these celestial bodies. Some of these missions even successfully passed by comets to collect dust and particles. However, a NASA mission that reached an asteroid, touched its surface, collected samples from it, and managed to bring those samples back to Earth. Until today, this has happened only once. The name given to this mission, OSIRIS-REx. Although not frequently discussed, this important mission opened one of the most significant doors leading humanity back to its past, to the very moment of creation. Its journey to the asteroid named Bennu cannot be described merely as a technological achievement. It was in fact a scientific turning point. However, this journey, of course, did not proceed entirely without problems. Unexpected discoveries, unforeseen challenges, and risky maneuvers were encountered. So, what did the OSIRIS-REx mission accomplish? What exactly were NASA's expectations from this mission? What did this small asteroid named Bennu tell us? Welcome to my channel, Jekio. Let's take a detailed look together at the fascinating story of OSIRIS-REx. The mission named OSIRIS-REx was one of the key missions of NASA's New Frontiers program. Perhaps this program didn't have enormous budgets, but it still encompassed extremely ambitious scientific missions and analyses. The Frontiers program also included missions like Juno and New Horizons, which had the potential to fundamentally change our perspective of our solar system. Yes, from the very beginning, the OSIRIS-REx mission was an important member of a highly prestigious club. NASA launched its spacecraft in September 2016. This journey was expected to last at least more than 2 years. It embarked on a journey requiring patience. The journey that began in 2016 finally reached the asteroid named Bennu on December 3, 2018. In the initial phase, the first task was quite simple: to position itself near the asteroid, image it, analyze its surface, and map it. It's important to know that OSIRIS-REx was not an ordinary observation vehicle. What made OSIRIS-REx unique was that it also contained a return mission to collect samples. It wouldn't just observe from a distance. It would also focus on Bennu's surface, collect material from there, and bring that material back to our Earth. This mission was a first for NASA. For the first time, a sample would be taken from the surface of an asteroid. Perhaps an important small detail should also be noted. Japan's space agency, JAXA, had previously accomplished and succeeded in such missions with Hayabusa and Hayabusa 2. However, for NASA, this mission was a complete challenge, and the possibility of failure was also a consideration. So why was there a need to study these asteroids? Why were they expending so much effort? Was it worth it? Because asteroids are ancient and the most primitive remnants found in the solar system. They are, in fact, primitive leftovers from the raw materials that drifted through space before planets were even born. In another definition, they are important building blocks of planets. This makes them extremely important, because within their cores, they hold crucial, unaltered information about conditions billions of years ago. An even more interesting piece of information is that asteroids are not just composed of rock and metal. Almost all of them contain water-related minerals, clay structures, and even organic molecules. Of course, hydrocarbons, amino acids, and other compounds critical for the emergence of life. All of these are found on asteroids in a way whose mystery we have not yet fully unraveled. This raises another question. Could some of the water found on Earth and some of the necessary chemical components for life have been transported to our planet via asteroids? Of course, we have meteorites. Thousands of space rocks that have fallen to our Earth have been analyzed to date. However, these meteorites are exposed to extreme temperatures as they enter our atmosphere. This heat alters their structures, causing delicate molecules to break down. In the phase after they land, They become contaminated through contact with Earth's water, oxygen, and microorganisms. Therefore, what was truly important for scientists was a sample taken directly from an asteroid, one that had not yet entered the atmosphere, had never been in the Earth environment. The primary mission of OSIRIS-REx was exactly to find this. OSIRIS-REx's arrival at Bennu in 2018, although it is a near-Earth asteroid, was not as easy as one might think. Yes, Bennu may technically appear to be in an orbit near Earth. Nevertheless, reaching Bennu did not seem very simple. On the contrary, this asteroid moved on a path that did not exactly match Earth's orbital map, and its gravity was almost non-existent. This required the SENT spacecraft to adjust its speed with extreme precision. If it accelerated a bit, it could miss Bennu. If it slowed down a bit too much, it could lose its balance. For this reason, OSIRIS-REx's arrival at Bennu took time and lasted almost over 2 years. During this long journey, the spacecraft performed numerous orbital maneuvers, meticulously adjusted its speed, and finally focused on the target. What was truly interesting was that the OSIRIS-REx team had an idea of what Bennu was like. Before the spacecraft even embarked on its journey, realistic simulations about Bennu's shape and surface were created by analyzing radar observations conducted from Earth. OSIRIS-REx approached Bennu quite closely, and the images it sent became increasingly clear. When the team receiving the images examined the photographs, they experienced great surprise and realized this. The simulations done on Earth were almost completely identical. Bennu looked as predicted, appearing approximately 500 meters in diameter with its distinctive spinning top-like shape. This odd-looking shape was estimated to have formed over time due to low gravity and the asteroid's rapid rotation. But the surprising shock emerged when the surface details were examined. Bennu was not covered with a smooth regolith layer, like a fine sand, as scientists had predicted. On the contrary, its surface was filled with large rock fragments. Some of the rocks were found to be 58 meters wide and 20 meters high, enormous boulders appearing almost the size of a football field alone. Some rocks had blocks at least the size of a horse. Asteroids had previously been described as rubble piles, but what was discovered on Bennu took this definition to another level. It was literally a cluster of randomly piled rock pieces, barely held together by the force of gravity. This vista showed that the sample collection mission was part of a more challenging task than the team had anticipated. Bennu looked interesting and mysterious. It was a carbonaceous asteroid, but it seemed to belong to the rarely encountered B-type class. These characteristics placed Bennu in the same class as another asteroid in the solar system, Pallas. It even gave the impression that Bennu and Pallas could be fragments that broke off from a violent collision they experienced in the past. Other analyses and measurements suggested that Bennu could be a very rare F-type asteroid. This strengthened the possibility that it could have come from another body belonging to the Pallas family, about 55 kilometers in diameter, as a result of a collision. Considering both scenarios, one thing was clear and certain. Bennu had performed a gravitational dance through numerous, uncertain interactions until it reached its current orbit. Bennu's distinct orbit makes it valuable not only scientifically, but also for planetary defense. Among the asteroids we have detected and have information about to date, it appears to be one of the most likely to collide with Earth. However, this probability still seems extremely low. According to analyses from 2014, even the likelihood of a potential collision around the year 2175 was approximately 1 in 2700. So, there didn't seem to be a reason for alarm. But it was still a target that needed to be monitored carefully. Before OSIRIS-REx could permanently enter Bennu's orbit, it had to take safety measures. It needed to analyze whether there were tiny satellites wandering around the asteroid or free-floating debris fragments. Such pieces could create deadly dangers for the spacecraft. Therefore, OSIRIS-REx performed some maneuvers around Bennu, scanning the asteroid's surroundings and measuring the weak gravity of this small celestial body. It was finally deemed safe and was placed in an orbit at an altitude of 1.75 kilometers. This was actually a record. Bennu was the smallest celestial body that a spacecraft had ever orbited. The gravitational force of such a tiny body was so weak that it took OSIRIS-REx almost 62 hours to complete one orbit around Bennu. However, this slow and very sensitive orbit was a good thing for scientists. because it made it easier for the spacecraft to scan the asteroid's surface millimeter by millimeter as it orbited. So the result? It was one of the highest resolution surface mapping studies ever conducted for any celestial body. OSIRIS-REx was not limited to just taking photographs. It also analyzed Bennu's chemical composition, mineralogy, geological history, and dynamic behaviors. The aim was not only to identify interesting-looking spots, but to fully analyze and understand the scientific context of the data to be collected. During these preliminary scans, something new was discovered that greatly excited scientists. Hydrated minerals appeared on Bennu's surface. This meant there were clay structures that had interacted with water. This was quite surprising. The reason was that it was thought a celestial body as small as Bennu would not be large enough to retain water on its own. The implication was this: not Bennu itself, but the parent body from which it formed once had liquid water. Bennu was a fragment that separated from this parent body, and the traces of water were trapped within the clay minerals. However, while all these discoveries were being made, the main big problem was emerging and becoming clearer. Collecting a sample from Bennu's surface appeared to be a rather dangerous mission. Scientists were trying to find an area approximately 25 meters in diameter, free of large boulders, with fine-grained material for the sampling mission. But such a place didn't seem to exist on Bennu. After months of detection and discussions, 4 optimal points on the surface were identified. These regions were named Osprey, Kingfisher, Nightingale, and Sandpiper. Bird themes were intentionally used for the names. The name Bennu given to this asteroid was determined in a naming contest in 2012. The winner of the contest was a 3rd-grade student. This student thought that the long sampling arm of OSIRIS-REx resembled the slender, graceful neck of a heron and named the asteroid after the famous sacred bird Bennu from Egyptian mythology. NASA also chose to continue this bird theme. As OSIRIS-REx continued to orbit Bennu and map its surface, scientists began to realize that the asteroid was not a dead and static-looking rock as predicted. At first, everything seemed calm. Indeed, Bennu was neither a comet nor an active celestial body as known. However, this impression did not last very long. As the mission team meticulously analyzed the images, they detected different and strange-looking things on the surface. Sometimes, tiny particles were breaking off from Bennu's surface and scattering into space. These events didn't seem to be one-time occurrences. They repeated at certain times. Due to the asteroid's weak gravity, these particles didn't completely escape but actually orbited Bennu and then scattered back onto the surface. This situation both surprised and greatly excited scientists. Bennu was a much more active asteroid than they had anticipated. There were some possible reasons for Bennu shedding particles. One of them was Bennu's very fast rotation. This asteroid rotated around its own axis almost every 4.3 hours. This rotation speed, combined with its weak gravity, caused loose material on its surface to easily shift. Another possibility was the YWARP effect. Sunlight, due to the irregular shape of the body, creates a very tiny but continuous thrust force. Over millions of years, this effect accumulates and can gradually change the asteroid's rotation speed. OSIRIS-REx's analyses confirmed this, showing that this asteroid's rotation speed had increased over time. This increase had caused Bennu to accumulate rock particles in its equatorial region. Material breaking free from the center was slowly pushed towards the edges by the rotation. If this process continues long-term, it could cause a small asteroid like Bennu to completely disintegrate. The ejection events detected by OSIRIS-REx could be the first sign and indication of this process. While all these detections were being made, OSIRIS-REx was also preparing for its sample collection mission. This process lasted much longer than expected. The spacecraft wandered in Bennu's orbit for almost 505 days. During this time, Bennu's surface was scanned many times, potential risks were identified, and the safest scenarios for sampling were devised. Initially, for candidate regions that seemed safe were identified. However, upon more detailed analysis, serious differences were seen when these areas were compared. Some were very scientifically interesting but posed risks. Others seemed safer but risked not offering the expected scientific value. After much examination, the Nightingale region was chosen. The Nightingale region is a relatively young crater located in Bennu's northern hemisphere. Materials that had recently been exposed in the lower layers of this crater's surface were observed. This meant that samples taken from this region could not only be particles that had been on the surface for a long time and exposed to the space environment, but also newer materials, much closer to the asteroid's core. However, the Nightingale region had disadvantages. This region was quite small and surrounded by rocks. This required performing a very delicate maneuver during the touchdown. Before the OSIRIS-REx team took such a risk, they decided to make all preparations and conduct all necessary tests. The spacecraft was not planning to land directly on the surface. Before attempting the touchdown, it would rehearse the necessary maneuvers. The first rehearsal maneuver took place on April 15, 2020. OSIRIS-REx slowly descended towards Bennu and, at about 65 meters from the asteroid's surface, activated its thrusters to ascend again. The purpose of this maneuver was to test the spacecraft's navigation and analyze the thrust control with its laser altimeter. Everything proceeded as planned. The second rehearsal took place on August 11, 2020. In this rehearsal, the spacecraft approached within about 40 meters of the asteroid's surface. During this maneuver, OSIRIS-REx made small forward and backward movements to adjust its position. The system for analyzing surface rocks and avoiding them if necessary was successfully tested. And finally, the time approached. They were moving towards a point of no return. October 20, 2020. This important date was to be the very heart of the OSIRIS-REx mission. The spacecraft now had to act entirely on its own. Due to the signal delay with our Earth, human intervention in case of a problem was out of the question. Everything depended on pre-programmed software commands and, in a way, on the spacecraft's own decision-making systems based on machine learning. OSIRIS-REx approached Bennu and began a slow descent for touchdown. It prepared by raising its solar panels in a Y-shape upwards. The reason for this was to minimize the risk of hitting the rocky surface and to protect the panels from the dust likely to be stirred up shortly. And then, the spacecraft's arm for sample collection extended towards the surface. The moment the sampling arm touched Bennu's surface, nitrogen gas contained within it was released. Unfortunately, at that moment, something no one had predicted or expected happened. Bennu's surface wasn't hard. In fact, it offered almost no resistance. OSIRIS-REx's sampling arm descended into the asteroid and sank almost half a meter deep. Bennu's surface, contrary to expectations, was not solid. It appeared to be a porous structure. For example, if a human tried to step there, they would definitely sink in. When the spacecraft released the nitrogen gas, not just a few grams of dust as expected, but almost 6 tons of rock and regolith were thrown into the air. Bennu's weak gravity flung the scattered materials into space without any resistance. OSIRIS-REx's thrusters performed excellently throughout the mission, working powerfully. The spacecraft needed to quickly distance itself from this huge dust cloud. This maneuver, of course, had been planned from the beginning to the end. But the outcome was far beyond what was predicted. OSIRIS-REx had created a small but quite noticeable crater on the Bennu asteroid. When the spacecraft reached a safe distance, the team quickly checked the amount of sample collected. The target amount was 60 grams. But measurements determined that the collected sample was over 400 grams, even approaching 1 kilogram. The unexpectedly large amount of sample collected created an unforeseen problem. The sample container's lid was designed for a certain capacity and couldn't close completely. A small rock particle, however tiny, was preventing the lid from sealing, causing some material to leak out. Still, despite everything, they had achieved great success with this mission. OSIRIS-REx managed to safely place the sample container into the main capsule. Thus, the mission's most valuable cargo was secured. The spacecraft lingered in Bennu's orbit a while longer to observe if there were any changes on the surface. It was clearly detected that large boulders had shifted and there were noticeable changes on the surface. After OSIRIS-REx touched Bennu, nothing was the same as before. Of course, there was no reason for the spacecraft to stay there after completing its task. After OSIRIS-REx safely placed the collected sample head into its capsule, it didn't immediately end the mission. In fact, it remained in Bennu's orbit a bit longer, because this was an exploration, and scientists wanted to observe what effect this touch had on the asteroid's surface. This wait was not in vain. OSIRIS-REx orbited Bennu many times, checking the surface repeatedly. The result was quite interesting. It was observed that the surface regolith had shifted. The positions of some previously stationary large boulders had changed. For example, a boulder about 12 meters in diameter was found to have been hurled across the surface due to the interaction from the touch. These observations proved that Bennu had a very loose and fragile structure. And OSIRIS-REx had actually accomplished its mission. It didn't need to stay here. Now it was time for perhaps the most critical phase of this mission. It had to safely return the collected sample to Earth. On April 7, 2021, OSIRIS-REx winked at the Bennu asteroid for the last time. This was officially a farewell pass. Afterwards, it fired its thrusters, departed from Bennu, and set course for our Earth. This was a long journey. This return journey lasted approximately 2 years and 4 months. The spacecraft traveled nearly 1.9 billion kilometers. The time elapsed since the mission began was almost 7 years. 7 years of analyses, maneuvers, risks, and patience. All were for this moment. Finally, in September 2023, OSIRIS-REx approached Earth. But the spacecraft was not going to land on Earth directly yet. First, it would perform a meticulous and precise maneuver to release the sample capsule freely towards our planet. It itself would swing by Earth and continue on its way. On September 24, 2023, when it was about 100,000 kilometers away from our planet, OSIRIS-REx released this sample capsule. The sample capsule proceeded into Earth's atmosphere. Meanwhile, OSIRIS-REx fired its thrusters to adjust its course and safely departed without reaching Earth. In this way, both the capsule and the spacecraft safely completed their tasks. It was extremely important for the spacecraft to perform its maneuver at the correct time. The angle, speed, and direction at which the sample capsule was released into Earth's atmosphere were calculated with millimeter precision. The aim was for this capsule to land in an area of about 600 kilometers in the Utah desert. The size of this area was almost that of Chicago. In fact, when thought of on a space scale, it was an extremely tiny target. The sample capsule entered Earth's orbit at a speed of approximately 43,000 kilometers per hour. This speed was a record. It was determined to be the second fastest object to enter Earth's atmosphere. NASA's Stardust capsule holds the first place. During entry into Earth's orbit, the capsule reached an acceleration of 32 Gs. It's hard to even imagine this. For example, in daily life, we are subjected to 1 G. Many people lose consciousness even at accelerations around 4 or 5 Gs. Only astronauts experience about 3 Gs during launch. Fighter pilots, even with special suits, can only withstand 8-9 Gs. Of course, this capsule was built to withstand 32 Gs. Due to the speed and friction, the outer surface of the capsule reached a temperature of about 2,700 degrees Celsius. This is almost half the surface temperature of the Sun. Thanks to this extreme heat, the sample capsule was tracked by ground-based infrared telescopes. The reason it was still safe was the capsule's heat shield and its design. Thanks to this, the sample from Bennu inside the capsule was kept below 75 degrees Celsius despite the infernal temperatures outside. Over 99% of the kinetic energy was absorbed by the shield protecting the capsule. 2 minutes after entering Earth's atmosphere, when the capsule had decelerated sufficiently, the first parachute opened. The parachute ensured the capsule's stability. At an altitude of about 16 kilometers, radar systems locked onto the capsule and began tracking its descent. Just before landing, at about 1.5 kilometers, the second parachute opened. This reduced the capsule's descent speed to 18 kilometers per hour. It slowed down almost to bicycle speed. The sample capsule's landing in the Utah desert area was successful. Pre-positioned NASA recovery teams reached the area by helicopter, and the capsule was safely retrieved. The most important task to note was to prevent the sample from coming into contact with the Earth environment. To prevent contact, the capsule was not opened. It was placed in a hygienic environment and taken to the special laboratory at Johnson Space Center. But the interesting parts were just beginning. After the capsule landed in the Utah desert as planned, you might think the difficult part of the mission was over. But in fact, according to scientists, the most delicate and stressful process was just beginning. The reason was that this unique sample from the asteroid must not be exposed to Earth's environmental contamination in any way. Therefore, it was transported to Johnson Space Center in a controlled and safe manner. Special clean rooms were prepared for examination in a stable environment. The capsule's exterior was meticulously cleaned, and special care was taken to ensure no earthly dust particles or air seeped in. When the capsule was finally opened after all procedures were completed, the team opening it encountered a surprise. On the outer surface of the sampling head, that is, outside the capsule's core, about 70 grams of dark gray rock and dust particles were detected. This situation indicated that some of the samples collected from Bennu had been exposed to the outside due to the head not sealing completely during sampling. But still, this did not mean the mission was a failure. On the contrary, even this extra collected material was extremely important for scientists. Of course, these samples remaining on the outside were not as clean as the main sample. The reason was that the head was not completely sealed and had come into some contact with the external environment during the return to Earth. But the important thing was that the sample inside the main sample container appeared clean. An important factor ensuring this was that the main sample container was closed with an extremely complex and secure mechanism. There were a total of almost 35 fasteners. And of course, all of these had to be carefully removed without damaging the sample. This operation had to be performed inside a special glove box filled with nitrogen gas, following specific procedures. Working in such an environment was difficult, because during this operation, the air inside the boxes had to be replaced with neutral nitrogen gas. This would prevent the sample from reacting with oxygen or water vapor. Performing a delicate operation with limited mobility would take a considerable amount of time. Everything was proceeding smoothly as planned, until they encountered two screws. These two screws were literally locked by fine dust that had leaked from Bennu. This caused their threads to be damaged. Perhaps one of the most important samples humanity has ever retrieved from the orbit of the solar system was waiting for its mystery to be unraveled, held up by two small screws. The encountered problem caused a delay that lasted almost months. For NASA, such problems were not unsolvable. Solving this required extremely careful planning. Any new tool used to remove these two screws could contaminate the sample. Specifically to remove these two screws, a new tool was designed with special tips made of surgical quality, non-magnetic stainless steel. After all checks were made, it was decided to use the tool. And finally, the long-awaited moment had arrived. As a result of all these efforts, the new tool worked, and the capsule was opened. And they were met with something joyful. Inside the capsule was an asteroid sample more pristine and unaltered than anything seen before. A total of 51 grams of completely clean Bennu material was extracted. This sample amount was twice the target. This proved that the mission carried out by OSIRIS-REx was quite successful. The samples were examined one by one, their weights measured, and recorded by NASA. NASA's plan was to preserve at least 70% of this material for future study by scientists. The remaining portion would be shared with laboratories around the world. With this, the scientific discoveries were now beginning. Initial examinations determined that Bennu's regolith was dark-colored and carbon-rich. But this was just the beginning, because this material carried mysterious traces from the earliest moments of the solar system. Ongoing studies detected microscopic crystals, known as presolar grains. These crystals formed from other stars before our sun had even formed. This meant they were almost older than the sun itself. This material offers scientists important data about stars that existed before the solar system. But everything was not limited to these. The most important detail was this. When compared to all previously analyzed space rocks, these samples contained 6 times more supernova origin dust. This detection indicated that the solar system formed not just from the remnants of a single star, but from many. Scientists were eagerly awaiting the samples distributed to other laboratories. Because these samples contain not only the structure of the Bennu asteroid, but also the most fundamental clues about the origin of life. Examinations detected amino acids in these samples. As known, amino acids are the building blocks of proteins and are of fundamental importance for known life forms in the universe. Some of these amino acids had variants that are not found in biological systems, being entirely of extraterrestrial cosmic origin. This distinction is important. It shows us that these amino acids are not biological, but formed through natural processes in space. Of course, this was not the only finding. Traces containing nucleotide bases, which form the building blocks of DNA and RNA, were found in the sample structure. Sugar molecules and complex hydrocarbon structures, important conditions for life, were detected. The discovery made as a result of this mission strongly supports a frequently discussed idea. Could at least some of the necessary chemical components for life on Earth have been transported to our planet from space? Another important finding was Bennu's chemical diversity. Within the same sample, it was found that particles from many different regions had different chemical structures. This shows us that this sample was not just a single-type pile of rocks. The formation and diversity of such an asteroid show us how complex and dynamic the structure of the pre-formation solar system was. Scientists' perspective on this discovery is not only about understanding the past. It also offers us important clues and insights about the future. These samples from OSIRIS-REx are not just for uncovering the mysteries of the past. They are a critical and important step in finding the answer to the question of whether we are alone in the universe. The mission carried out by OSIRIS-REx is not only a scientific success, but also a beautiful example and indicator of humanity's exploration capacity in space. At the same time, the analysis of samples from Bennu in laboratories will lead to revolutionary new studies and ideas in fields such as planetary science, astrobiology, and cosmic chemistry in the future. In conclusion, OSIRIS-REx's mission is a true turning point in space research. For scientists, the importance of these missions fuels the excitement of solving the mysterious secrets in the depths of space, while for all humanity, it provides scientific data for answers to questions about our existential process, our place in the universe, how life spread, and where our origins lie. And it is also an incredibly exciting fact to know. These discoveries will be an important resource not only for our present, but also for future generations. Because the samples brought by Bennu, like an age-time capsule, shed light from 4.5 billion years ago. I am sending you this text as a total of 13 pages in Word. Please translate it into English without any abbreviation, without any changes, without adding any commentary, and in accordance with spelling rules.